The d block of the periodic table contains the elements of the groups 3 to 12, in which the d orbitals are progressively filled in each of the 4 long periods. The f block consists of elements in which 4f and 5f orbitals are progressively filled. They are placed in a separate panel at the bottom of the periodic table. The names transition metals and intertransition metals are often used to refer to the elements of D and F blocks respectively. There are mainly 4 series of the transition metals: 3D series, scandium to zinc for D series, yttrium to cadmium, 5D series, lanthanum and hafnium to mercury, and 6D series, which is actinium and elements from rutherfordium to copernicium. The 2 series of the intertransition metals, namely for F, cerium to lutetium, and 5F, thorium to lawrencium, are known as lanthanoids and actinoids respectively. Originally, the name transition metals was derived from the fact that their chemical properties were transitional between those of S and P block elements. Now, according to IUPAC, transition metals are defined as metals which have incomplete d subshell either in neutral atom or in their ions. Zinc, cadmium, and mercury of group 12 have full D10 configuration in their ground state, as well as in their common oxidation states, and hence are not regarded as transition metals. However, being the end members of the 3D for D and 5D transition series, respectively, their chemistry is studied along with the chemistry of the transition metals. The presence of partly filled D or F orbitals in their atoms makes transition elements different from that of the non-transition elements. Hence, transition elements and their compounds are studied separately. However, the usual theory of valence as applicable to the non-transition elements can be applied successfully to the transition elements also. Various precious metals, such as silver, gold, and platinum, and industrially important metals like iron, copper, and titanium belong to the transition metal series. The transition elements, D block. The D block occupies the large middle section of the periodic table flanked between S and P blocks in the periodic table. The d orbitals of the penultimate energy level of atoms receive electrons, giving rise to 4 rows of the transition metals. That is 3D, 4D, 5D, and 6D. In general, the electronic configuration of outer orbitals of these elements is N-1, D1 to 10, NS1 to 2, except for palladium, where its electronic configuration is 4D10, 5S0. The N-1 stands for the inner d orbitals, which may have 1 to 10 electrons, and the outermost NS orbital may have 1 or 2 electrons. However, this generalization has several exceptions because of very little energy difference between N-1, d, and NS orbitals. Furthermore, half and completely filled sets of orbitals are relatively more stable. A consequence of this factor is reflected in the electronic configurations of chromium and copper in the 3D series. For example, consider the case of chromium, which is 3D54S1 configuration instead of 3D44S2. The energy gap between the two sets, 3D and 4S, of orbitals is small enough to prevent electron entering the 3D orbitals. Similarly, in case of copper, the configuration is 3D10 4S1 and not 3D9 4S2. The electronic configurations of outer orbitals of zinc, cadmium, mercury, and copernicium are represented by the general formula N-1, D10, and S2. The orbitals in these elements are completely filled in the ground state, as well as in their common oxidation states. Therefore, they are not regarded as transition elements. The d orbitals of the transition elements protrude to the periphery of an atom more than the other orbitals, that is, S and P. Hence, they're more influenced by the surroundings, as well as affect the atoms or molecules surrounding them. In some respects, ions of a given d-n configuration, where n equals 1 to 9 have similar magnetic and electronic properties. With partly filled d orbitals, these elements exhibit certain characteristic properties, such as display of a variety of oxidation states, formation of colored ions, and entering into complex formation with a variety of ligands. The transition metals and their compounds also exhibit catalytic property and paramagnetic behavior. There are greater similarities in the properties of the transition elements of a horizontal row in contrast to the non-transition elements. However, some group similarities also exist. Physical properties. Nearly all the transition elements display typical metallic properties such as high tensile strength, ductility, malleability, high thermal and electrical conductivity, and metallic luster. With the exceptions of zinc, cadmium, mercury, and manganese, they have one or more typical metallic structures at normal temperatures. The transition metals, with the exception of zinc, cadmium, and mercury, are very hard and have low volatility. Their melting and boiling points are high. The high melting points of these metals are attributed to the involvement of greater number of electrons from N-1, d, in addition to the ns electrons in the interatomic metallic bonding. In any row, the melting points of these metals rise to a maximum at D5, except for anomalous values of manganese and technetium, and fall regularly as the atomic number increases. They have high enthalpies of atomization. The maxima at about the middle of each series indicate that one unpaired electron per d orbital is particularly favorable for strong interatomic interaction. In general, greater the number of valence electrons, stronger is the resultant bonding. Since the enthalpy of atomization is an important factor in determining the standard electrode potential of a metal, metals with very high enthalpy of atomization, that is, very high boiling point, tend to be noble in their reactions. The metals of the second and third series have greater enthalpies of atomization than the corresponding elements of the first series. This is an important factor in accounting for the occurrence of much more frequent metal bonding in compounds of the heavy transition metals. In general, ions of the same charge in a given series show progressive decrease in radius with increasing atomic number. This is because the new electron enters a d orbital each time the nuclear charge increases by unity. It may be recalled that the shielding effect of a d electron is not that effective. Hence, the net electrostatic attraction between the nuclear charge and the outermost electron increases and the ionic radius decreases. The same trend is observed in the atomic radii of a given series. However, the variation within a series is quite small. An interesting point emerges when atomic sizes of one series are compared with those of the corresponding elements in the other series. The curves of trends in atomic radii of transition elements show an increase from the first, 3D, to the second, 4D series of the elements, but the radii of the third, 5D, series are virtually the same as those of the corresponding members of the second series. This phenomenon is associated with the intervention of the 4f orbitals, which must be filled before the 5D series of elements begin. The filling of 4f before 5d orbital results in a regular decrease in atomic radii called lanthanoid contraction, which essentially compensates for the expected increase in atomic size with increasing atomic number. The net result of the lanthanoid contraction is that the second and the third D series exhibit similar radii. Examples: zirconium 160 picometers, hafnium 159 picometers, and have very similar physical and chemical properties, much more than that expected on the basis of usual family relationship. The factor responsible for the lanthanoid contraction is somewhat similar to that observed in an ordinary transition series, and is attributed to similar cause, that is, the imperfect shielding of one electron by another in the same set of orbitals. However, the shielding of one 4f electron by another is less than that of 1d electron by another, and as the nuclear charge increases along the series, there is fairly regular decrease in the size of the entire 4F in orbitals. The decrease in metallic radius, coupled with increase in atomic mass, results in a general increase in the density of these elements. Thus, from titanium, atomic number 22, to copper, atomic number 29, the significant increase in the density may be noted. Ionization enthalpies. There is an increase in ionization enthalpy along each series of the transition element from left to right due to an increase in nuclear charge which accompanies the filling of the inner d orbitals. These values of the first three ionization enthalpies of the first series of transition elements show that the successive enthalpies of these elements do not increase as steeply as in the case of non-transition elements. The variation in ionization enthalpy along a series of transition elements is much less in comparison to the variation along a period of non-transition elements. The first ionization enthalpy, in general, increases, but the magnitude of the increase in the second and third ionization enthalpies for the successive elements is much higher along a series. The irregular trend in the first ionization enthalpy of the metals of 3D series, though of little chemical significance, can be accounted for by considering that the removal of one electron alters the relative energies of 4s and 3d orbitals. When d-block elements form ions, s electrons are lost before n-1d electrons. As we move along the period in 3D series, we see that nuclear charge increases from scandium to zinc, but electrons are added to the orbital of inner subshell, that is 3d orbitals. These 3d electrons shield the 4s electrons from the increasing nuclear charge somewhat more effectively than the outer shell electrons can shield one another. Therefore, the atomic radii decrease less rapidly. Thus, ionization energies increase only slightly along the 3D series. The doubly or more highly charged ions have d-n configurations with number 4s electrons. A general trend of increasing values of second ionization enthalpy is expected as the effective nuclear charge increases because 1d electron does not shield another electron from the influence of nuclear charge because d orbitals differ in direction. However, the trend of steady increase in second and third ionization enthalpy breaks for the formation of manganese 2 plus ion and iron 3 plus ion respectively. In both the cases, ions have d5 configuration. Similar breaks occur at corresponding elements in the later transition series. The three terms responsible for the value of ionization enthalpy are attraction of each electron towards nucleus, repulsion between the electrons, and the exchange energy. Exchange energy is responsible for the stabilization of energy state. Exchange energy is approximately proportional to the total number of possible pairs of parallel spins in the degenerate orbitals. When several electrons occupy a set of degenerate orbitals, the lowest energy state corresponds to the maximum possible extent of single occupation of orbital and parallel spins, Hund's rule. The loss of exchange energy increases the stability. As the stability increases, the ionization becomes more difficult. There is no loss of exchange energy at D6 configuration. Manganese plus ion has 3d5-4s1 configuration, and configuration of chromium plus ion is d5. Therefore, ionization enthalpy of manganese plus ion is lower than chromium plus ion. In the same way, iron 2 plus ion has d6 configuration and manganese 2 plus ion has 3d5 configuration. Hence, ionization enthalpy of iron 2 plus ion is lower than the manganese 2 plus ion. In other words, we can say that the third ionization enthalpy of iron is lower than that of manganese. The lowest common oxidation state of these metals is +2. To form the M2 plus ions from the gaseous atoms, the sum of the first and second ionization enthalpy is required in addition to the enthalpy of atomization. The dominant term is the second ionization enthalpy, which shows unusually high values for chromium and copper, where M plus ions have the D5 and D10 configurations respectively. The value for zinc is correspondingly low as the ionization causes the removal of one 4s electron, which results in the formation of stable D10 configuration. The trend in the third ionization enthalpies is not complicated by the 4s orbital factor and shows the greater difficulty of removing an electron from the D5 manganese 2 plus ion and D10 zinc 2 plus ions. In general, the third ionization enthalpies are quite high. Also, the high values for third ionization enthalpies of copper, nickel, and zinc indicate why it is difficult to obtain oxidation state greater than 2 for these elements. Although ionization enthalpies give some guidance concerning the relative stabilities of oxidation states, this problem is very complex and not amenable to ready generalization. Oxidation states. One of the notable features of transition elements is the great variety of oxidation states these may show in their compounds. The elements which give the greatest number of oxidation states occur in or near the middle of the series. Manganese, for example, exhibits all the oxidation states from +2 to +7. The lesser number of oxidation states at the extreme stems from either too few electrons to lose or share, scandium, titanium, or too many d electrons, hence fewer orbitals available in which to share electrons with others, for higher valence, copper, zinc. Thus, early in the series scandium 2 is virtually unknown and titanium 4 is more stable than titanium 3 or titanium 2. At the other end, the only oxidation state of zinc is +2. No d electrons are involved. The maximum oxidation states of reasonable stability correspond in value to the sum of the s and d electrons up to manganese, followed by a rather abrupt decrease in stability of higher oxidation states. So that the typical species to follow are iron 2 and 3, cobalt 2 and 3, nickel 2, copper 1 and 2, and zinc 2. The variability of oxidation states, a characteristic of transition elements, arises out of incomplete filling of d orbitals in such a way that their oxidation states differ from each other by unity. For example, vanadium 2, vanadium 3, vanadium 4, vanadium 5. This is in contrast with the variability of oxidation states of non-transition elements, where oxidation states normally differ by a unit of 2. An interesting feature in the variability of oxidation states of the d-block elements is noticed among the groups 4 through 10. Although in the p-block the lower oxidation states are favored by the heavier members due to inert pair effect, the opposite is true in the groups of d-block. For example, in group 6, molybdenum 6 and tungsten 6 are found to be more stable than chromium 6. Thus, chromium 6 in the form of dichromate in acidic medium is a strong oxidizing agent, whereas molybdenum trioxide and tungsten trioxide are not. Low oxidation states are found when a complex compound has ligands capable of p-acceptor character in addition to the sigma bonding. For example, in nickel tetracarbonyl NiCO4 and iron carbonyl FeCO5, the oxidation state of nickel and iron is 0. Trends in the M2 plus and M standard electrode potentials. Observing the thermochemical parameters related to the transformation of the solid metal atoms to M2 plus ions in solution and their standard electrode potentials, we can identify the unique behavior of copper. Having a positive electrode potential accounts for its inability to liberate hydrogen from acids. Only oxidizing acids, nitric, and hot concentrated sulfuric, react with copper, the acids being reduced. The high energy to transform copper, solid, to Cu2+, aqueous, is not balanced by its hydration enthalpy. The general trend towards less negative electrode potential values across the series is related to the general increase in the sum of the first and second ionization enthalpies. It is interesting to note that the value of electrode potential for manganese, nickel, and zinc are more negative than expected from the trend. Trends in the M3+ and M2+ standard electrode potentials. An examination of the electrode potential of M3+ and M2+ value shows the varying trends. The low value for scandium reflects the stability of scandium 3+, which has a noble gas configuration. The highest value for zinc is due to the removal of an electron from the stable D10 configuration of zinc 2+. The comparatively high value for manganese shows that manganese 2+, D5, is particularly stable, whereas comparatively low value for iron shows the extra stability of iron 3+, D5. The comparatively low value for vanadium is related to the stability of vanadium 2+. Trends in stability of higher oxidation states. On observing the stable halides of the 3D series of transition metals, we note that the highest oxidation numbers are achieved in titanium tetrahalides TiX4, where X can be chlorine, bromine, or iodine. Vanadium pentafluoride VF5 and chromium hexafluoride C are F6. The +7 state for manganese is not represented in simple halides, but manganese trioxide fluoride NO3F is known, and beyond manganese, no metal has a trihalide except iron trihalide FeX3 and cobalt trifluoride COF3. The ability of fluorine to stabilize the highest oxidation state is due to either higher lattice energy, as in the case of cobalt trifluoride COF3, or higher bond enthalpy terms for the higher covalent compounds. For example, vanadium pentafluoride VF5 and chromium hexafluoride CrF6. Although vanadium +5 is represented only by vanadium pentafluoride VF5, the other halides, however, undergo hydrolysis to give oxohalides, vanadium 3 oxide VOX3. Another feature of fluorides is their instability in the low oxidation states, for example VX2, where X could be chlorine, or bromine, or iodine, and the same applies to copper X. On the other hand, all copper 2 halides are known except the iodide. The stability of copper 2+ aqueous, rather than copper plus aqueous, is due to the much more negative hydration enthalpy of copper 2+ aqueous than copper plus, which more than compensates for the second ionization enthalpy of copper. The ability of oxygen to stabilize the highest oxidation state is demonstrated in the oxides. The highest oxidation number in the oxides coincides with the group number and is attained in scandium trioxide SC2O3 to manganese 7 oxide N2O7. Beyond group 7, no higher oxides of iron above iron trioxide Fe2O3 are known, although ferrates 6 FeO4 2- are formed in alkaline media, but they readily decompose to Fe2O3 and oxygen. Besides the oxides, oxidations stabilize vanadium 5 as deoxyvanadium ion VO2+, V4 as VO2+, and titanium 4 as TiO2+. The ability of oxygen to stabilize these high oxidation states exceeds that of fluorine. Thus, the highest manganese fluoride is MnF4, whereas the highest oxide is Mn2O7. The ability of oxygen to form multiple bonds to metals explains its superiority. In the covalent oxide Mn2O7, Each manganese is tetrahedrally surrounded by oxygen, including a manganese-oxygen-manganese bridge. Chemical reactivity and E0 values. Transition metals vary widely in their chemical reactivity. Many of them are sufficiently electropositive to dissolve in mineral acids, although a few are noble, that is, they're unaffected by single acids. The metals of the first series, with the exception of copper, are relatively more reactive and are oxidized by 1 molar concentration of hydrogen plus ions, though the actual rate at which these metals react with oxidizing agents like hydrogen ion, H+, is sometimes slow. For example, titanium and vanadium, in practice, are passive to dilute non-oxidizing acids at room temperature. The E0 values for M2+ and M indicate a decreasing tendency to form divalent cations across the series. This general trend towards less negative E0 values is related to the increase in the sum of the first and second ionization enthalpies. It is interesting to note that the E0 values for manganese, nickel, and zinc are more negative than expected from the general trend. Whereas the stabilities of half-filled D subshell, D5, in manganese 2+ ion and completely filled D subshell, D10, in zinc are related to their E0 values. For nickel, E0 value is related to the highest negative enthalpy of hydration. An examination of the E0 values for the redox couple M3+ and M2+ shows that manganese 3 ion and cobalt 3 ions are the strongest oxidizing agents in aqueous solutions. The ions titanium 2+ ion, vanadium 2+ ion, and chromium 2+ ion are strong reducing agents and will liberate hydrogen from a dilute acid. Magnetic properties. When a magnetic field is applied to substances, mainly two types of magnetic behavior are observed: diamagnetism and paramagnetism. Diamagnetic substances are repelled by the applied field, while the paramagnetic substances are attracted. Substances which are attracted very strongly are said to be ferromagnetic. In fact, ferromagnetism is an extreme form of paramagnetism. Many of the transition metal ions are paramagnetic. Paramagnetism arises from the presence of unpaired electrons, each such electron having a magnetic moment associated with its spin angular momentum and orbital angular momentum. For the compounds of the first series of transition metals, the contribution of the orbital angular momentum is effectively quenched and hence is of no significance. For these, the magnetic moment is determined by the number of unpaired electrons and is calculated by using the spin-only formula, which is mu equals to square root of n multiplied by n plus 2, where n is the number of unpaired electrons and mu is the magnetic moment in units of Bohr magneton. A single unpaired electron has a magnetic moment of 1.73 Bohr magnetons. The magnetic moment increases with the increasing number of unpaired electrons. Thus, the observed magnetic moment gives a useful indication about the number of unpaired electrons present in the atom, molecule, or ion. Formation of colored ions. When an electron from a lower energy d orbital is excited to a higher energy d orbital, the energy of excitation corresponds to the frequency of light absorbed. This frequency generally lies in the visible region. The color observed corresponds to the complementary color of the light absorbed. The frequency of the light absorbed is determined by the nature of the ligand. Formation of complex compounds. Complex compounds are those in which the metal ions bind a number of anions or neutral molecules, giving complex species with characteristic properties. The transition metals form a large number of complex compounds. This is due to the comparatively smaller sizes of the metal ions, their high ionic charges, and the availability of d orbitals for bond formation. Catalytic properties. The transition metals and their compounds are known for their catalytic activity. This activity is ascribed to their ability to adopt multiple oxidation states and to form complexes. Vanadium oxide, in contact process, finely divided iron, in Haber's process, and nickel, in catalytic hydrogenation, are some of the examples. Catalysts at a solid surface involve the formation of bonds between reactant molecules and atoms of the surface of the catalyst. First-row transition metals utilize 3d and 4s electrons for bonding. This has the effect of increasing the concentration of the reactants at the catalyst surface and also weakening of the bonds in the reacting molecules. The activation energy is lowering. Also, because the transition metal ions can change their oxidation states, they become more effective as catalysts. Formation of interstitial compounds. Interstitial compounds are those which are formed when small atoms like hydrogen, carb, or nitrogen are trapped inside the crystal lattices of metals. They are usually non-stoichiometric and are neither typically ionic nor covalent. For example, titanium carbide, manganese nitride, etc. The formulas quoted do not, of course, correspond to any normal oxidation state of the metal. Because of the nature of their composition, these compounds are referred to as interstitial compounds. The principal physical and chemical characteristics of these compounds are as follows. 1. They have high melting points, higher than those of pure metals. 2. They're very hard. Some borides approach diamond in hardness. 3. They retain metallic conductivity. 4. They are chemically inert. Alloy formation. An alloy is a blend of metals prepared by mixing the components. Alloys may be homogeneous solid solutions in which the atoms of one metal are distributed randomly among the atoms of the other. Such alloys are formed by atoms with metallic radii that are within about 15% of each other. Because of similar radii and other characteristics of transition metals, alloys are readily formed by these metals. The alloys so formed are hard and have often high melting points. The best known are ferrous alloys. Chromium, vanadium, tungsten, molybdenum, and manganese are used for the production of a variety of steels and stainless steel. Alloys of transition metals with non-transition metals, such as brass, copper zinc, and bronze, copper tin, are also of considerable industrial importance. Oxides and oxoanions of metals. These oxides are generally formed by the reaction of metals with oxygen at high temperatures. All the metals except scandium form MO oxides, which are ionic. The highest oxidation number in the oxides coincides with the group number and is attained in scandium trioxide or scandia, Sc2O3, to demanganese heptoxide N2O7. Beyond group 7, no higher oxides of iron above Fe2O3 are known. As the oxidation number of a metal increases, ionic character decreases. In the case of manganese, Mn2O7, demanganese heptoxide is a covalent green oil. Even chromium trioxide, CrO3, and vanadium pentoxide V2O5 have low melting points. In these higher oxides, the acidic character is predominant. Potassium dichromate K2CR2O7. Potassium dichromate is a very important chemical used in leather industry and as an oxidant for preparation of many azo compounds. Dichromates are generally prepared from chromate, which in turn are obtained by the fusion of chromite or FeCr2O4 with sodium or potassium carbonate in free access of air. The yellow solution of sodium chromate is filtered and acidified with sulfuric acid to give a solution from which orange sodium dichromate can be crystallized. Sodium dichromate is more soluble than potassium dichromate. The latter is therefore prepared by treating the solution of sodium dichromate with potassium chloride. Orange crystals of potassium dichromate crystallize out. The chromates and dichromates are interconvertible in aqueous solution depending upon pH of the solution. The oxidation state of chromium in chromate and dichromate is the same. The chromate ion is tetrahedral, whereas the dichromate ion consists of two tetrahedra sharing one corner with chromium, oxygen, chromium bond angle of 126 degrees. Sodium and potassium dichromates are strong oxidizing agents. The sodium salt has a greater solubility in water and is extensively used as an oxidizing agent in organic chemistry. Potassium dichromate is used as a primary standard in volumetric analysis. Acidified potassium dichromate will oxidize iodides to iodine, sulfide to sulfur, tin 2 to tin 4, and iron 2 salts to iron 3. The full ionic equation may be obtained by adding the half reaction for potassium dichromate to the half reaction for the reducing agent. Potassium permanganate KMnO4. Potassium permanganate is prepared by fusion of manganese dioxide MnO2 with an alkali metal hydroxide and an oxidizing agent like potassium nitrate KNO3. This produces the dark green potassium manganate K2MnO4, which disproportionates in a neutral or acidic solution to give permanganate. Commercially, it is prepared by the alkaline oxidative fusion of manganese dioxide NO2 followed by the electrolytic oxidation of manganate VL. In a laboratory, a manganese 2 ion salt is oxidized by peroxidous sulfate to permanganate. Potassium permanganate forms dark purple, almost black, crystals which are isostructural with those of potassium perchlorate KClO4. The salt is not very soluble in water, 6.4 grams per 100 grams of water at 293 Kelvin, but when heated it decomposes at 513 Kelvin. It has two physical properties of considerable interest: its intense color and its geomagnetism along with temperature-dependent weak paramagnetism. These can be explained by the use of molecular orbital theory, which is beyond the present scope. The manganate and permanganate ions are tetrahedral. The bonding takes place by overlap of p orbitals of oxygen with d orbitals of manganese. The green manganate is paramagnetic because of one unpaired electron, but the permanganate is diamagnetic due to the absence of unpaired electron. Acidified permanganate solution oxidizes oxalates to carbon dioxide, iron 2 to iron 3, nitrites to nitrates, and iodides to free iodine. The hydrogen ion concentration of the solution plays an important part in influencing the reaction. Although many reactions can be understood by consideration of redox potential, kinetics of the reaction is also an important factor. Permanganate at H equals 1 should oxidize water, but in practice the reaction is extremely slow unless either manganese 2 ions are present or the temperature is raised. Uses of potassium permanganate. Besides its use in analytical chemistry, potassium permanganate is used as a favored oxidant in preparative organic chemistry. Its uses for the bleaching of wool, cotton, silk, and other textile fibers, and for the decolorization of oils are also dependent on its strong oxidizing power. The inner transition elements, F block. The F block consists of the two series, lanthanoids, the 14 elements following lanthanum, and actinoids, the 14 elements following actinium. Because lanthanum closely resembles the lanthanoids, it is usually included in any discussion of the lanthanoids for which the general symbol Ln is often used. Similarly, a discussion of the actinoids includes actinium besides the 14 elements constituting the series. The lanthanoids resemble one another more closely than do the members of ordinary transition elements in any series. They have only one stable oxidation state, and their chemistry provides an excellent opportunity to examine the effect of small changes in size and nuclear charge along a series of otherwise similar elements. The chemistry of the actinoids is, on the other hand, much more complicated. The complication arises partly owing to the occurrence of a wide range of oxidation states in these elements. The lanthanoid's electronic configuration. It may be noted that atoms of these elements have electronic configuration with 6s2 common, but with variable occupancy of 4f level. However, the electronic configurations of all the tripositive ions, the most stable oxidation state of all the lanthanoids, are of the form 4Fn, n equals 1 to 14 with increasing atomic number. Atomic and ionic sizes. The overall decrease in atomic and ionic radii from lanthanum to lutetium, the lanthanoid contraction, is a unique feature in the chemistry of the lanthanoids. It has far-reaching consequences in the chemistry of the third transition series of the elements. The decrease in atomic radii, derived from the structures of metals, is not quite regular as it is regular in M3+ ions. This contraction is, of course, similar to that observed in an ordinary transition series and is attributed to the same cause, the imperfect shielding of one electron by another in the same subshell. However, the shielding of one 4f electron by another is less than 1d electron by another with the increase in nuclear charge along the series. There is fairly regular decrease in the sizes with increasing atomic number. The cumulative effect of the contraction of the lanthanoid series, known as lanthanoid contraction, causes the radii of the members of the third transition series to be very similar to those of the corresponding members of the second series. The almost identical radii of zirconium, 160 picometer, and hafnium, 159 picometer, a consequence of the lanthanoid contraction, account for their occurrence together in nature and for the difficulty faced in their separation. Oxidation states. In the lanthanoids, lanthanum 2 and lanthanide 3 compounds are predominant species. However, occasionally +2 and +4 ions in solution or in solid compounds are also obtained. This irregularity, as in ionization enthalpies, arises mainly from the extra stability of empty, half-filled or filled F subshell. Thus, the formation of cerium-4 is favored by its noble gas configuration, but it is a strong oxidant reverting to the common +3 state. The E0 value for cerium-4+ ion and cerium-3+ ion is +1.74 V, which suggests that it can oxidize water. However, the reaction rate is very slow and hence cerium-4 is a good analytical reagent. Praseodymium, neodymium, terbium, and dysprosium also exhibit +4 state, but only in oxides, molybdenum, MO2. Europium Eu2+ is formed by losing the two s electrons, and its F7 configuration accounts for the formation of this ion. However, Europium-2+ is a strong reducing agent, changing to the common +3 state. Similarly, ytterbium Yb2+, which has F14 configuration, is a reductant. Terbium-4 has half-filled F orbitals and is an oxidant. The behavior of samarium is very much like europium, exhibiting both +2 and +3 oxidation states. General characteristics. All the lanthanoids are silvery white soft metals and tarnish rapidly in air. The hardness increases with increasing atomic number, samarium being steel hard. Their melting points range between 1000 to 1200 K, but samarium melts at 1623 K. They have typical metallic structure and are good conductors of heat and electricity. Density and other properties change smoothly except for europium and ytterbium and occasionally for samarium and thulium. Many trivalent lanthanoid ions are colored both in the solid state and in aqueous solutions. Color of these ions may be attributed to the presence of F electrons. Neither lanthanum 3 plus ion nor lutetium 3 plus ion shows any color, but the rest do so. However, absorption bands are narrow, probably because of the excitation within F level. The lanthanoid ions other than the F0 type, lanthanum 3 plus and cerium 4 plus, and the F14 type, ytterbium 2 plus and lutetium 3 plus, are all paramagnetic. The first ionization enthalpies of the lanthanoids are around 600 kilojoules per mole, the second about 1,200 kilojoules per mole, comparable with those of calcium. The variation of the third ionization enthalpies indicates that the exchange enthalpy considerations, as in 3d orbitals of the first transition series, appear to impart a certain degree of stability to empty, half-filled, and completely filled orbitals F level. This is indicated from the abnormally low value of the third ionization enthalpy of lanthanum, gadolinium, and lutetium. In their chemical behavior, in general, the earlier members of the series are quite reactive, similar to calcium, but with increasing atomic number, they behave more like aluminium. The metals combine with hydrogen when gently heated in the gas. The carbides LN3C, LN2C3, and LNC2 are formed when the metals are heated with carbon. They liberate hydrogen from dilute acids and burn in halogens to form halides. They form oxides M2O3 and hydroxides MOH3. The hydroxides are definite compounds, not just hydrated oxides. They're basic like alkaline earth metal oxides and hydroxides. The best single use of the lanthanoids is for the production of alloy steels for plates and pipes. A well-known alloy is misc metal, which consists of a lanthanoid metal, about 95%, and iron, approximately 5%, and traces of sulfur, carbon, calcium, and aluminium. A good deal of misc metal is used in magnesium-based alloy to produce bullets, shell, and lighter flint. Mixed oxides of lanthanoids are employed as catalysts in petroleum cracking. Some individual LN oxides are used as phosphors in television screens and similar fluorescing surfaces. The actinoids. The actinoids include the 14 elements from thorium to lawrencium. The actinoids are radioactive elements, and the earlier members have relatively long half-lives. The latter ones have half-life values ranging from a day to 3 minutes for lawrencium, atomic number Z equals 103. The latter members could be prepared only in nanogram quantities. These facts render their study more difficult. Electronic configurations. All the actinoids are believed to have the electronic configuration of 7s2 and variable occupancy of the 5f and 6d subshells. The 14 electrons are formally added to 5f, though not in thorium, atomic number equals 90. But from protactinium onwards, the 5f orbitals are complete at element 103. The irregularities in the electronic configurations of the actinoids, like those in the lanthanoids, are related to the stabilities of the F0, F7, and F14 occupancies of the 5f orbitals. Thus, the configurations of americium and curium are radon, 5f77s2, and radon, 5f76d, 17s2. Although the 5f orbitals resemble the 4f orbitals in their angular part of the wave function, they're not as buried as 4f orbitals, and hence 5f electrons can participate in bonding to a far greater extent. Ionic sizes. The general trend in lanthanoids is observable in the actinoids as well. There is a gradual decrease in the size of atoms, or M3 plus ions, across the series. This may be referred to as the actinoid contraction, like lanthanoid contraction. The contraction is However, greater from element to element in this series, resulting from poor shielding by 5f electrons. Oxidation states. There is a greater range of oxidation states, which is in part attributed to the fact that the 5f, 6d, and 7s levels are of comparable energies. The actinoids show in general +3 oxidation state. The elements in the first half of the series frequently exhibit higher oxidation states. For example, the maximum oxidation state increases from +4 in thorium to +5, +6, and +7 respectively in protactinium, uranium, and neptunium, but decreases in succeeding elements. The actinoids resemble the lanthanoids in having more compounds in +3 state than in the +4 state. However, +3 and +4 ions tend to hydrolyze. Because the distribution of oxidation states among the actinoids is so uneven and so different for the former and later elements, it is unsatisfactory to review their chemistry in terms of oxidation states. General characteristics and comparison with lanthanoids. The actinoid metals are all silvery in appearance, but display a variety of structures. The structural variability is obtained due to irregularities in metallic radii, which are far greater than in lanthanoids. The actinoids are highly reactive metals, especially when finely divided. The action of boiling water on them, for example, gives a mixture of oxide and hydride in combination with most nonmetals takes place at moderate temperatures. Hydrochloric acid attacks all metals, but most are slightly affected by nitric acid owing to the formation of protective oxide layers. Alkalis have no action. The magnetic properties of the actinoids are more complex than those of the lanthanoids. Although the variation in the magnetic susceptibility of the actinoids with a number of unpaired 5f electrons is roughly parallel to the corresponding results for the lanthanoids, the latter have higher values. It is evident from the behavior of the actinoids that the ionization enthalpies of the early actinoids, though not accurately known, are lower than for the early lanthanoids. This is quite reasonable, since it is to be expected that when 5f orbitals are beginning to be occupied, they will penetrate less into the inner core of electrons. The 5f electrons will therefore be more effectively shielded from the nuclear charge than the 4f electrons of the corresponding lanthanoids. Because the outer electrons are less firmly held, they are available for bonding in the actinoids. A comparison of the actinoids with the lanthanoids, with respect to different characteristics as discussed above, reveals that behavior similar to that of the lanthanoids is not evident until the second half of the actinoid series. However, even the early actinoids resemble the lanthanoids in showing close similarities with each other and in gradual variation in properties, which do not entail change in oxidation state. The lanthanoid and actinoid contractions have extended effects on the sizes, and therefore, the properties of the elements succeeding them in their respective periods. The lanthanoid contraction is more important because the chemistry of elements succeeding the actinoids are much less known at the present time. Some applications of D and F block elements. Iron and steels are the most important construction materials. Their production is based on the reduction of iron oxides, the removal of impurities, and the addition of carbon and alloying metals, such as chromium, manganese, and nickel. Some compounds are manufactured for special purposes, such as titanium oxide for the pigment industry and manganese dioxide, and O2 for use in dry battery cells. The battery industry also requires zinc and nickel-cadmium. The elements of Group 11 are still worthy of being called the coinage metals, although silver Ag and gold Au are restricted to collection items, and the contemporary UK copper coins are copper-coated steel. The silver UK coins are a copper and nickel alloy. Many of the metals and/or their compounds are essential catalysts in the chemical industry. Vanadium pentoxide V2O5 catalyzes the oxidation of sulfur dioxide in the manufacture of sulfuric acid. Titanium tetrachloride TiCl4 with trimethyl aluminium AlCH3. 3 forms the basis of the Ziegler catalyst used to manufacture polyethylene, polythene. Iron catalysts are used in the Haber process for the production of ammonia from nitrogen and hydrogen mixtures. Nickel catalysts enable the hydrogenation of fats to proceed. In the Wacker process, the oxidation of ethene to ethanol is catalyzed by palladium chloride PdCl2. Nickel complexes are useful in the polymerization of alkynes and other organic compounds, such as benzene. The photographic industry relies on the special light-sensitive properties of silver bromide AgBr.